Hi, everyone. So my name's Leena. I'm a applied mathematician turned derivatives quant turned data scientist. And part of the reason why I was interested in making the most recent transition was that I wanted to work on problems that affect real people. So in DebiasML, I developed a practical yet effective methodology for reducing bias in machine learning algorithms. So some of you might recall that last year, Amazon was forced to scrap an AI recruiting tool it was using because it was shown to be biased against women. This is just one example of the wider problem of bias in AI. So machine learning is being used at an ever-increasing rate to automate decisions that were previously made by humans, and many of these decisions can have life-changing impacts for people. So it's important to be fair, but the argument for reducing bias isn't just ethical, it's financial too. There have been multiple studies that have shown that teams that are more diverse in race and gender significantly outperform teams that aren't. So what does an unbiased algorithm look like? Well, in simple terms, you can think of it as being symmetric. So in an algorithm that, say, decides who gets a job, the probability of being hired if you're male should be equal to the probability of being hired if you're female. So to tackle this problem, we need some data. And for this, I used census income data, which tells us for each person in the population whether they earn over 50K or not. There's about 33,000 data points with 14 features, and the data set's imbalanced, so that 3/4 of the population earn less than 50K. Also, 2/3 are male and 86% are white. So to see how biased a machine learning algorithm could be, I trained a classifier to predict whether or not people earn over 50K, and then made predictions on a test set. Sure enough, I found that the probability of earning more than 50K was 2.8 times the probability of earning more than 50K for men was 2.8 times the probability of earning more than 50K for women. So the US Equal Employment Opportunity Commission states that if the bias factor, and I'm going to call this thing a bias factor, falls outside of the range from 0.8 to 1.25, your algorithm is officially considered to be biased. So at least as a starting point, we want our method to reduce the bias factor to below 1.25. To tackle this problem, I took a high-level view. In any supervised machine learning algorithm, there are 3 key components you could change: the data you train your model on, the model you fit to the data, and the success metric you use to judge your model's performance. So in this case, the bias is coming from the data, so the approach I take in DebiasML is to fix the data. And I do this using oversampling, which is a technique that's used extensively for solving data imbalance problems, but has not been extensively used for the issue of bias. When I did this, I found it worked really well. So in these graphs, the top row shows the distribution of predictions on the test set when training on the original data, and the bottom row shows the same when training on the oversampled data. And you can see that the bias factors have reduced significantly, and importantly below 1.25, with only a small degradation of 2% in accuracy and F1 score. So clearly this method works, but how does it compare to other methods people are currently using? So the kind of most publicized method at the moment for reducing bias is using generative adversarial networks, or GANS. And here we have the same slide again, but this time on the top we have the distribution of predictions using GANS. And you can see that the performance when compared with DebiasML is similar on bias reduction and accuracy, but DebiasML achieves a significantly higher F1 score. This means that DebiasML overall is much better at finding the people we're interested in finding. In this case, it's people who earn over 50K, but in another example, you could imagine that it might be people you want to hire. So predictive performance isn't the only dimension DebiasML beats GANS on. DebiasML is model agnostic, it's transparent, it's 10 times faster to train, and it's easier to train because there are fewer additional parameters. It's not perfect though. Multi-dimensional oversampling is tricky. The number of distinct pools from which you need to oversample increases exponentially with the number of sensitive features. So that's it from me. I hope you found this informative. Thanks for listening.